Then on the menu today. Last time we talked about reinforcement learning, and I introduced a Markov decision process. This was the first directed probabilistic graphical model that we saw. And because this is an interesting and important class of models, I wanted to give you another example application of a directed probabilistic graphical model. And I thought an interesting example application could be robot localization. And this is what I want to start with. I will briefly talk about mapping, and then to again pick up on reinforcement learning, I want to talk about path planning for robots with a stochastic component. And I've picked all these because, well, I think robotics is one of the cooler problems these days. And so I've also so one of the more famous books in this realm, I have the cover of this book somewhere in one of my slides. There it is this one here. And it was interesting to me to see that many of the ideas in the book only came about in the mid-90s, late 90s, or early 2000s. So, the math is more or less at the level of what we've seen in this course, but it came into the world really very late. And by the way, the first author, Thun, you may have read his name in various contexts. So he was the leader of the team that won the first DARPA challenge for a car that could drive through a desert autonomously. And these days he's CEO of a company called Kitty Hawk. And supposedly in February this year, we'll see, they will bring out their first product, which will be either a flying motorcycle or a flying car. Okay, and now here's part of my loose motivation for today, that such systems need to know where they are, and this is why localization is an important problem. Okay, I want to give you first a very broad overview of problems, and then we will zoom in and discuss various flavors of this problem. So what are the kind of questions people ask? One problem is called localization or pose estimation. That means I am a robot, I have a map, somebody has just switched me on, and I now need to figure out where I am, even if in between, my batteries ran out or something. Yeah. This problem is relatively easy, and we'll discuss it today. The next problem is also relatively easy. I am a robot. I have a perfect compass and a very high resolution GPS sensor built in. So I know my pose. I am acquiring measurements, and I need to build a map of my surroundings. We will not discuss it today, but this is also a pretty easy task. The next one is actually super hard for robots. I am a robot. I have a sensor. And I need to simultaneously figure out where I am and build a map of the environment. So this is simultaneous localization and mapping, or SLAM for short. And I think we are proof, that the problem is solvable in principle. And of course, there are many algorithms by now that do that somehow. We are perfectly capable of, walking around in a flat, in an apartment, even if it's the first time that we're in there, and to know where we are. And if it's a big apartment, then we might take the wrong door the first one or two times, but eventually we build our map and we know where we are. And but this problem, a hen and egg kind of problem, where we have neither the hen nor the egg initially, is much, much more difficult for computers. Then there is the problem of making decisions, either of a single robot, for example, how to what is the optimal path to achieve some goal, or how, or if the robot has locomotion built in, what are the optimal poses it should visit to build a reliable map in as few steps as possible. And sometimes it's not just one agent involved, but several agents, and then this is the realm of cooperative decision making. And reinforcement learning, which we discussed last time, plays a role in quite a few of these problems here. Good, let's start with localization. So I have a map, I have a sensor, I need to figure out where I am. I'm first going to give you the intuition using figures copied from this book, and then we'll go through the math. I will start with a movie here. So we start with, if I can interrupt this. This is an algorithm which has a random component, and we start with just initializing uniformly particles. Each particle thinks, well, I could be the true robot position. And marked in green is the actual true robot position, and shown in blue are the readings of its range sensor. And so the range sensor, it's supposed to measure the distance to the closest boundary or wall. And as you see, it's not perfect. Yeah? So this range here, some of these rays should have been longer, others should have been shorter. I'm not sure why some of the rays are too short. Maybe they hit a paper basket or something. Some of the rays which are too long can be too long because maybe there was a mirror on the wall or there was total reflection on the wall. So anyway, the measurements are noisy. Yeah? And then the robot is moved a little bit, or maybe it is not moved, but it receives a command to proceed a little bit, and it takes a second set of measurements. And now many of these tentative beliefs that we previously held are no longer, cannot be upheld. So, for example, there were particles in corners of room, and if truly the robot had been in a corner of the room, then two of the range measurements should have been extremely short, and none of them was extremely short. So we have somehow boiled down the number of possible hypotheses. And this goes on and on. And now something interesting happens. There are still now a few positions left that are related by symmetry, between which even at this point the robot cannot decide. And now comes my favorite part. The robot enters or is entered into a room, and you see that this floor map is a little bit symmetric. So we have this narrow room where the robot actually enters with a couch or desk or something at the end of it. But there's the second room where you see the second red blob, which has a similar shape and also similarly has something set up at its end. And now the robot goes in there and now finally acquires measurements, namely of this blob that's very close to the true robot there, which rule out the location in the second room. And at this point, this wrong beliefs vanish, and now all belief particles here concentrate on the true position of the robot. Okay, so what I've shown you here is the output of a concrete algorithm that we will discuss later that solves the localization problem. Now here a bit more schematically and in more detail. We have initially a robot located close to one of the three doors, and we have here on the y-axis we have the belief that the robot is at a certain position x, and the prior belief is non-informative. So we have, if you see the thick black line here, This is meant to indicate a uniform belief. The robot has no idea where it is. Now, the robot makes a measurement, and this measurement tells the robot, I am close to some door. So we see here the probability of the measurement z given all possible locations x. And even at these points here, because the sensor readings are noisy, this probability is not 0, but it's some low value. And then close to the 3 doors, we get high values. Well, because the robot sensors tell it probably is close to a door. Then the prior belief, which was uniform, is multiplied with this likelihood, and we get this curve in black, which you see at the bottom. And at this point, after this point in time, the robot moves 3 steps to the right. So from here to here, if you see what has happened with the belief, it has shifted to the right because the robot has moved to the right by 3 meters. But also, if you look closely at these peaks, they have become wider. Any suggestions why they have become wider?
You have some uncertainty about the exact movement.
Mm-hmm, exactly. So when you tell the robot to, go straight by 3 meters, it may in reality go 3 meters and 1 centimeter, or just short of 3 meters, etc. This is why they've become wider. We have some uncertainty between what we tell the robot to do or what it wants to do, its action, and what is the actual outcome. Okay, so there's the new belief. At this point, the robot makes a new measurement, and the measurement tells the robot, well, I'm close to a door. So if we only ask what is the likelihood of this measurement given the position, we get this red curve. And now we combine this belief and this likelihood by multiplying them. So these two are multiplied, and the result is shown here. And well, we now have one position with a much, much higher peak than all the others, which here in this nice example happens to be the true position. And then the robot moves a few further steps to the right, and again the whole distribution shifts to the right, and again we have some spread because there is some uncertainty in the motion model, and so on. Yeah? So the robot iteratively acquires sensor readings and updates its internal belief and performs actions. And over time, hopefully, we'll have a nice and sharp peak at the position where it truly is. Okay, and like I said, the figure here is taken from, like most figures I will show today, from this book here. Okay, let's do this more quantitatively. So we want a probabilistic graphic model. It will be a directed one relating our poses and actions and the readings. So at each point in time, there is a true pose. This is the pose or the location. This pose, the pose at time 2, both depends or is related to the previous pose, but also on some action that led up to this time point. And this action is known. So I'm shading the variable here to say this is observed. And the action could either be input from a remote control. So if the robot is a drone, then maybe somebody has been steering it on remote control, or the robot may have decided itself what those actions are. Then the robot also knows a map, M, so I'm putting this as observed. And then we have these sensor readings or measurements, R1 at time 1, which depend both on the true pose and on the map, of course, R2 and R3. And then this thing goes on and on in time. So this was pose or location, this here was the action. These here were the sensor readings. That's why I used R. R for range also, in case it's a range sensor. And we have the map. Okay, whenever you see the map, if I ignore the map which has been observed, then the structure on the top. So whenever you see a directed probabilistic graphical model, which looks like this, so you have some. Oh, the range has also been observed. That's important. So these are the measurements, which I'm dashing here, have been observed. Whenever you have the following fundamental structure, that you have a hidden state, which emits observations, and the observations, at least some of them, are available. Then this is a very important class of directed probabilistic graphical model. This is called a hidden Markov model. If the hidden state is discrete, or it is a Bayesian sequential filtering model, if we make no comment about what the structure of the internal state is. In the special case that the internal state depends linearly on the previous state, and and if the observation likelihoods are Gaussian, then this is called a Kalman filter. Just curious, who has studied the hidden Markov model before? And the Kalman filter. Okay. Good. So both are super important. The Kalman filter, in a nutshell, is what made space flight possible. So to track the rockets that put satellites into our orbit and so on, this was only possible thanks to the Kalman filter, because we have noisy measurements and we still need to figure out where is the object actually. And hidden Markov model, well, we'll see one use of it today, but it has also been used for decades very successfully in speech processing before recurrent neural networks took over. And there are whole libraries on either of these methods. If you want to look it up in a single book, I would recommend the book by Barber, which is called Bayesian Reasoning and Machine Learning. But there are many other books that also describe these concepts. Okay, so today we want these poses given the measurements. So we want the marginals. And now there are different questions that we could ask. So we could ask, for example, for the distribution of the true pose at time small t, given given all actions, so from 1 to capital T, and given all sensor readings from 1 to capital T. And this problem is also known as smoothing. In smoothing, when we want to, let's say, we want to estimate the marginal of my pose at this time here, I take into account both past and future measurements. For this to work, obviously, I must have, this works only offline. Yeah? So this works only after the fact. So this would be an offline procedure. But sometimes, or very often, you want to work online. You want to know where am I now without having the measurements from the future available. So here in the online case, we're interested in probability of xt given only the actions up to this point in time, so 1 to small t, and the readings from the past and the present, but not the future. And this is also known as filtering. So for example, there is talk about Kalman smoothing and Kalman filtering, and that's the difference. Okay, and now we will work in this online setting here. So first of all, we will use we will rewrite this using Bayes' theorem as the joint distribution. Times 1 over p of only the actions and the sensor readings. So the rule I've been using here simply is that the probability of A and B is the probability of A given B times the probability of B. And I've just used this with a few more variables here than just A and B. Okay. Now, this term here, we're interested in the pose, and this term here does not depend on the pose. So this is needed to get a properly normalized marginal out, but when we ask the question, where is the robot, this is not going to change our answer. So we will simply ignore this for now. And ignoring it, we will look at this joint distribution. So I'm good. Now, the probabilistic graphical model that we looked at, if you remember a directed probabilistic graphical model, what this tells us is the following. So the probability here of X, A, R, and M would be a product of RT given X, T, and M. then we have a probability of xt depending on at and xt minus 1. Rx, and then we have all the probabilities of the actions. And finally, we have the probability of the map. So this would be the factorization that my directed probabilistic graphical model specifies. And then I need a corner case with, just a moment, so P1, P of x1 given a1 and x0, I just define as P of x1 given a1. You have a question? Okay. Yeah. Mm-hmm. Good. So, as I argued last time, such a factorization makes for great savings in specifying a model. But of course, it needs to be a decent model for reality. And the argument that we make here in this Markovian model is that, for example, the current pose only depends on the previous pose and on the action taken, and it does not depend on, the pose before that. Pose here needs to be understood in general terms. Maybe I should say state more generally. The state could only be the coordinates of the robot at some point in time, or it could be the coordinates and the velocity. Yeah? So to get more of a ballistic model, if we want one. Good. Now I've been writing this down. So this thing here was shorthand for the probability of. Wait, do I squeeze this in? Of x1, so of all states and all actions and all readings. And now this equation here, except for the map that we have not written explicitly anywhere because the map is known, it's observed. So this term here starts to look similar to the one that I had written at the very bottom of the page. Yeah. Similar but not quite, because here we just have a single state, and at the very top we had a joint probability distribution involving all states. So to get rid of the extra variables that we don't want, we integrate them out, we marginalize over them. So here I integrate out all variables x1 up to t minus 1. But we can maybe already guess by looking at the structure of the probabilistic graphical model that it's not necessary for each of my xt's to integrate over all previous states. So I will claim, and we'll see in a few lines that this is the case, that it's okay to only have a joint of the present state xt and the previous state xt minus 1. And to only integrate out this previous state. So I've omitted all the other variables. Okay, so we want to calculate the thing on the right-hand side. And to this end, we'll use Bayes' theorem. So I will write that this is the probability of R. Okay, let me say again what I'm doing here. I'm writing that the probability of, let's say, A and B and C, the joint, can be written as the probability of C given A and B times the probability of A and B. But the probability of A and B, I can again factorize. I can say this is the probability of A given B times probability of B. So this is the formula that I'm going to use here. So I'm starting by writing the probability of R conditioned on the others. Can you maybe please close the door so that not the whole world will have that recorded? Thank you. So we'll make this conditioned on xt minus 1 and on xt and on all actions and on the readings only 1 to t minus 1. And now the right-hand side, we say this is probability xt given xt minus 1, actions 1 through t and r 1 through t minus 1. To t and r1 through t minus 1. Okay, and now we can read off, so on the one hand, terms that do not depend on xt minus 1 at all, we can pull out. And on the other hand, we can now use the probabilistic graphical model. So we can say, for example, this one here simplifies greatly. We can say that the probability of my sensor reading at time t only depends on x at time t, but given xt, it's conditionally independent of xt minus 1 and the previous actions and rewards. Okay, so I scroll up to this point here, and what this says here is that, for example, this random variable is conditionally independent of all these other ones given that one. And this is the kind of conditional independence relation that you can read off such a directed probabilistic graphical model, and I have not proven these conditional independent relations here, and I don't have time to, but you can find them, for example, in this book by Barber or in the book by Bishop, for example. Good, so in colloquial terms, my reading at time t depends only on the position, or it depends only on the pose at time t, but not on the pose in the previous time step. If my sensor makes instantaneous measurements, I believe this is an argument you can even believe qualitatively. Okay, And now this no longer depends on xt minus 1, so I can not have it inside the integral, but have it outside the integral. And then xt only depends on xt minus 1 and on the action at time t, but not on the previous actions and not on the previous sensor readings. And for the last term, we have xt minus 1 depending on 1 through t minus 1 and r1 through t minus 1. And now I've omitted the probability of a t here. Which I write separately because they're independent. And because it does not depend on my integration variable, I pull it out of the integration. Okay. Now, if we look at this thing here, we see that the same pattern appears here. This is the same quantity, just at the previous time step. So wherever I had a t written, I now have a t minus 1 written. And so we can write this as recursion, and I'm calling this term here alpha of xt minus 1. And up here it would be alpha of xt. And what we see now is a pattern where this thing here is called the prediction. Or the predictor step. And this thing here is called the correction. So what we have here is the old belief. Here my old belief is propagated to the current time. And then this propagated old belief now becomes updated with my measurement. And so this is an example of an important class of algorithms, a predictor-corrector algorithm. And this is the same pattern that we have in hidden Markov models and in Kalman filters. But it has a, it has a well-founded probabilistic explanation of this whole algorithm. And then, by the way, so this boring term here, which does not depend on the pose. It is, however, a term smaller one. It can be a very small term. And this can lead to numerical problems. When we now iterate this equation here and we multiply with these small numbers again and again. So it's a good idea to replace this by some possibly large constant. We can do that because anyway we had ignored the proper normalization up here. There also we had simply ignored this term. And so what we can do is we can compute these unnormalized beliefs. And if we then normalize them in the end, then we get out proper marginals. Yeah, so this alpha, so if we use this equation here, so iterating this gives us an unnormalized marginal. In our robot example here, we would say that, I'm using a different color now, again this would be the old belief. Then this thing here would be the motion model. So it tells us the probability of our new pose given the old pose and the action. Sorry. It gives us the probability of the new pose given the old pose and the action. And then we have here a measurement model. Which tells us how likely is a given sensor reading given a particular pose and implicitly given the map, which I have not explicitly conditioned on here. And the motion model, by the way, is what is shown by a concrete example in this picture here. The motion model usually would give us densities. Here these densities are represented in terms of particles. So the robot starts here. So we have motion model samples in this picture. Robot starts here and is told to walk 1 meter straight. And then the robot does walk, so it points in this direction initially. It does walk 1 meter straight, but because maybe one wheel is a little bit larger than the other, or because there is some dirt on the floor, we don't end up with a perfect point, but with a small spread of possible locations. And then we tell it to go straight by another meter, and we end up here, and we get a bigger possible set of poses, and we tell it to go another meter. Then we tell it to turn left by 90 degrees. And now you see that this distribution resulting here is a little bit skewed. And that's because this particular robot turns by stopping one wheel and keep on turning with the other. And that has a particular kind of error pattern that this results in. So it's told to turn 90 degrees and then walk or proceed straight by 1 meter, and we get this, proceed by another meter, turn left. And after all these commands, so after executing this 10 or so commands, the possible positions of this robot are anywhere in here. And this is simply because it's difficult to predict with 100% accuracy where exactly the robot will be if we don't correct for any errors made in between. So that would be the possible set of locations if we had no measurements at all, if we only used the motion model. But now, in addition, of course, so that would be propagating the old belief, and this is why in the picture before the distributions became wider over time. But now, of course, we have measurements that we also throw into the calculation. So here we go. Same picture that we saw before. The initial belief is uniform. Our measurement tells us that we are somewhere close to a door. So the likelihood of this measurement, which I have called R and which here is called Z. So I would have called this probability of R given X. The likelihood for me measuring, or for the robot measuring that is close to a door and its true position being here is low, 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 high, low, etc. Then this is multiplied with the prior belief, and because the prior belief was uniform or uninformative, this does not change anything at all. Then the robot performs an action. We invoke the motion model, and this is why the expected locations of the robot, so everything has shifted, but also everything has become broader. Then we make the new measurement, we multiply the likelihood with the prior belief, we obtain the updated belief, and so on and so on. Okay? That's it already. I have pictures from two possible implementations here. The first one is simply in terms of a dense grid. So on the right, so on the left is the picture that we've just seen. On the right would be a grid world representation. And you see it's the identical thing. So the measurement likelihood is still continuous, but my beliefs are now expressed as histograms. And provided the bins are fine enough, this does not change much. Or here's another representation in terms of the so-called particle filter, where we sample from the distribution. So the prior belief, for example, is represented by particles that were simply sampled uniformly, from some Poisson process here over the entire domain. Then these particles are reweighted by the measurement. But because all particles should have the same weight, we now resample, which means particles of low weight die out and particles of large weight can have offspring. And then there's another measurement, there's another reweighting, and so on. And this particle picture here is the kind of picture that we saw in the animation that I showed you initially, where we had these red dots representing the possible locations of the robot. Good. Questions? Yeah?
When you did this calculation stuff, in the first step, you still have an integral over all different, all different times. In the second step, only the previous time, you said this will become apparent in memory. Is this because the previous state only depends on its predecessor, and since the predecessor has been integrated out, the next one?
Yes, so what we see is that we get this equation where alpha of x depends only on the predispose xt minus 1. And now we could, of course, compute this term here explicitly by doing all the other integrations. But it's the old dynamic programming story that we would need, let's say, for the pose 14 and the pose 15. We could do all the inner integrations both times, but the results would be identical. So we do them just once and propagate.
Yeah, my question is about an earlier step. So the second equation side.
This equality here.
Yes, exactly.
Mm-hmm.
So is that justified by the process later, or is that something which should be clear already up there?
So this is true for the probabilistic graphical model that we've seen. Of course, not true in general. You know? And if I now invoke the definition of alpha xt minus 1, and so on, then I get the equation on top. Yeah? So what I did from here to here, I said, let's take a leap of faith and see if we get out something workable, and we did, and that I use as justification for having written both equations here with an equality sign. But the fundamental reason this is an equality is only thanks to the model having this particular structure here. More questions? Yeah.
Could you explain one more time the part of the filter?
Mm-hmm.
Like how to sample and we wait?
Okay. So question was about the particle filtering. The thing is that if we have a very large domain, then maybe our histogram becomes too big to keep in memory. Another typical modeling approach that I have not talked about here is to try and use either a single Gaussian, that would be a Kalman filter, or a mixture of Gaussians, that would be the unscented Kalman filter. But ultimately, we want to be able to model arbitrary distributions. And in particle filtering, arbitrary distributions are represented by discrete particles. But as the distribution changes over time, we have just a fixed budget of particles, let's say 1,000. And we want the density of these particles to mimic or to represent the underlying continuous density. Yeah? So this is why the particles and each particle, after resampling, we don't want weighted particles. We want the particles through their distribution to represent the continuous distribution. So in the first step, uniform density really means I can sample a Poisson process. Yeah? So I just take the uniform distribution and draw samples and then scale them to lie between here and there, between the limits of the domain. Then my likelihood here, my measurement likelihood, I can now evaluate my likelihood at each of my 1,000 particles. So for 1,000 particles, I only do 1,000 evaluations, and the result has been indicated here. And now I could draw from these particles with resampling. So I could compute the cumulative distribution function of these weighted particles. So let me do this. Huh? So if I zoom in way, then the cumulative distribution function increases by 1 every time that I observe a particle. You know where I'm going, yeah? And then if I have a heavy particle, I make, so somewhere here, I make, so here it's flat, and I make a big jump in my cumulative distribution function because it was a heavy particle. And now this has a lot of staircases, yeah? This CDF. And so what I can do, I can smooth this CDF ever so slightly. Yeah? So this curve here, I make it a little bit smoother. And then from this smooth curve, I sample by taking the uniform distribution between 0 and 1, and for each random number that I get, I take the inverse CDF, and that gives me a new particle. And if I do this 1,000 times, I get 1,000 particles. I get more in the areas where I had this important particles. I get few. I get a depletion elsewhere. And the one fudge parameter that I have in here is how much do I want to smooth. If I smooth too much, then I may smooth over the finer points in my distribution. If I smooth too little, then I will sample particles from identical or almost identical positions. And overall, the smoothing needs to be a good match between how complicated is my distribution and what is the number of particles that I have available. So this is the one fudge factor, the amount of smoothing. Okay, but then in the end, this is what you saw in the movie, one particle for each possibility of where the robot could be. And if some of these other particles don't die out, well, if you're asked to make a final decision, then you simply look for the area where there are most particles in a small volume. Just by the way, there's also a kidnapped robot problem where the idea is that at any time the robot can be teleported, but without knowing about it. So the robot happily walks around, makes its measurements, and suddenly somebody lifts it and puts it down elsewhere, and the robot has no sensors to notice that it was lifted. And to become robust against such teleportation, it is a good idea to have some random particles in a few places, just to avoid being too sure or being completely deterministic in the decision of where the robot is. Yeah?
So the particles themselves don't gather any information from the other particles, right? So it's basically like a multi-agent system that is based on movement based on probability until the result makes there, of course.
Let me think. Yes, you're right. They are independent. It's like, each particle has its own interpretation of what's going on or its own truth.
So they all just have the simple movement rule and don't interact. Right?
Yeah, they don't interact, yes. Mm-hmm. Yeah?
Is the mark sufficient to script in this scenario? For example, if and also the velocity also encoded into action output. So then in this scenario, maybe the present velocity also depends on the previous one, not the last velocity in the last time step.
So for to model ballistic systems, the Markov model is perfectly fine. You just need to inflate the definition of your state space. So you could, for example, have a state which has the location and the bearing, so in which direction the robot is oriented, and you could have its velocity, or for the bearing, its angular velocity, and you could have its current acceleration, for example. And if you want, you could even have higher moments, just they become unreliable to measure. But this Markov description as such, for ballistic systems, it's fine. More questions?
So the particles change based on the observation from the sensor.
the weight of the particle changes, and then after resampling, their distribution changes, yes?
But the distribution changes because we want to make it smoother.
We want more particles. You see, we don't want, here we have weighted particles, but we want to represent the distribution by particles that all have equal probability. Yeah? So we replace these few important particles by many particles of the same weight. And in this picture, it's two things. There's the resampling and then there's the shifting because the robot has performed an action walk to the right.
Okay, so instead of having a small amount of important particles, we have many more dense particles that are less important.
Yes. So I can do two things. Yeah. So one is I can either sample from the CDF that I showed with its staircase and everything. Yeah. And then each of these particles undergoes the stochastic motion. Yeah? So if I sample such a heavy particle 5 times, and then if I tell the robot to go about 3 meters to the right, then some particles will walk further than others, which is why you get a spread here. Or equivalently, you can smooth the CDF and then sample from it. It's the same result. Yeah?